about a polynomial-time algorithm for the ground state of 1D gapped local Hamiltonians.
Thanks, Martin. Mic is on, right? Okay. So I want to thank the organizers, Steve and the other organizers, for inviting me to speak here. It's a real pleasure. I've also been a participant in this whole semester from the start, so I also thank the organizers of the larger semester for having me here. It's really been a pleasure in these workshops. This is the third workshop that we've been having. They really give a rhythm to the semester. They've been very enjoyable, so it's a pleasure to be speaking in front of you. So even though this is the quantum algorithms workshop, I'm maybe going to disappoint some of you and going to talk about the classical algorithm, but this classical algorithm for a well-motivated quantum problem. So let me start by giving a little bit of introduction, general motivation. Of course, you're all familiar with the fact that the classical description size of quantum systems increases exponentially as you consider more and more qubits or more and more particles. And of course, this is the one thing that we're trying to take advantage of when we design algorithms, quantum algorithms that have speed-ups over the best classical algorithms. There's also a bit of a curse because it means that, at least in the generic setting, quantum mechanical systems require exponentially many parameters to be described and also to be simulated. So that's a difficulty for experimental physics. And of course, Feynman knew this already. He's credited for being the first to observe that one of the main applications of quantum computers would actually be to simulate quantum mechanical systems because they give a rich class of problems for which a priori we don't have efficient classical simulation, so we'll use quantum computers in order to simulate quantum systems. All right, but what if we don't have a quantum computer? Or maybe we do have a quantum computer. I don't know. I think there's a talk tomorrow, so we'll hear a lot more about this later. But even if we do have quantum computers, I want to argue that there's a very good motivation for studying the classical simulatability of quantum systems. Maybe the most basic motivation is that a priori classical simulation might give you much more information than a quantum simulation. For instance, you're trying to measure or observe a certain property of your system, and it might be hard to measure that property both on the original quantum system and also on the simulating quantum system. Whereas if you have a classical simulation, you might be able to access many more properties of your system. There's also more fundamental reasons why you'd want to come up with classical simulation. For instance, if you want to test that the laws of quantum mechanics apply to the systems that you're studying. So if you do a simulation of a quantum system with another quantum system, then the only thing that you're verifying is that, well, the laws that govern the one and the other system are sort of compatible. But you're not checking in any way that your quantum mechanics textbook is making the correct predictions. For this, we need to be able to come up with classical simulations. So even maybe deeper motivation is that every kind of quantum mechanical system that you manage to simulate classically, this is sort of, you're narrowing this exponential space down. You're saying, well, at least for this system, it only lives in a very small corner of the larger Hilbert space because I managed to find a classical description using my classical algorithm. So we're sort of probing the limits of this exponentiality here by trying to reduce the number of quantum problems that do not have, or we don't know how to classically simulate. So in the talk, I'm going to focus on just one very specific scenario, but it's a scenario of interest, I think, to experimentalists, or at least theoretical physics. So we're going to be looking at local Hamiltonians that act on the 1D chain of qubits. So these, that's my n qubits here. So think of those as being qubits. If you want just two-dimensional particles, this is fine. But the dimension might be a little bit higher. It might be 3, 4, maybe 10-dimensional particles, but constant dimensional. The asymptotic parameter is n, the number of qubits. And then we have our local Hamiltonian. So it's just a sum of n minus 1 terms here, such that it's a nearest neighbor Hamiltonian. So you can think of it in this way. Each of the h's acts only on two neighboring particles, and because it's in one dimensions, I can't have so many Hamiltonian terms. So I'll normalize these so that each hi is Hermitian. In fact, I'll just assume that it's positive and it has norm, operator norm at most 1. If you want, you can think of them as just being projections, 0, 1 eigenvalues, but that's, it's not required for the results that I'll describe. And so the main thing that we're interested in with this local Hamiltonian is its ground state. So that's the state that minimizes the energy, where the energy is defined as the overlap of the state with the Hamiltonian. So it's this expression there that I'll call E0. So the main goal is given as input a description of a local Hamiltonian H that's easy to specify classically. I have n matrices. Each of them is constant size, so there's a very simple description. We want to come up with a classical description of the ground state. And here I have to specify what I mean by classical description, because of course in general this ground state is a vector that's in d to the n dimensions, so we can't hope to specify all the amplitudes. So we have to come up with another kind of representation. The goal is that this representation be useful, so that we're able to compute all kinds of interesting properties of the ground state based on the classical representation. For instance, we want to be able to compute the energy, but maybe a little bit more. We want to be able to evaluate local observables, for instance. So for those of you who know the description that we're going to use are matrix product states. I think maybe most people are already familiar with them. If you're not, I'll sort of describe them a little bit later. So the question is whether we can solve, give a classical algorithm for this problem without actually, using a quantum. You could solve this quantumly, so cool down your system until it reaches the ground state. For this, you'd need a quantum computer, and also it might take a lot of time. So we're trying to achieve it using a classical algorithm. Okay, so in general, we know that we can't do this. This is a hard problem. It's known since the work of Kitaev that for general local Hamiltonians, approximating, not even finding a classical description of the ground state, but just approximating the ground state energy is QMA hard problem. And we know that it's still QMA hard for the kind of systems that I was describing that are one-dimensional on qubits. I think the record for the dimension of the qubits is maybe, I'm not sure actually, it used to be 11, maybe it's 7 now. Qubits it's easy, but at least as soon as you have a little bit higher dimensional particles, it becomes hard. We also know that it's hard for qubits, but then you need the graphs to be a little bit more complicated. I think Ashley might tell us much more about this in the next talk. What it means for us is that, in general, there's no hope for finding a classical description of the ground state of one-dimensional local Hamiltonians. All right. So it starts kind of badly, but there's also some positive signs. I mean, in practice, people who do physics know how to work with these local Hamiltonians. They have candidate-efficient classical representations, these matrix product states in one dimension, or higher dimensional generalizations of MPS that seem to work very well in practice. At least most systems that they're interested in, they can describe the ground state classically, and they can even find it. So there's this famous algorithm, DMRG, density matrix renormalization group algorithm, which in practice, given a local Hamiltonian, very efficiently finds a classical description of the ground state. Of course, we know that you couldn't have guaranteed polynomial time algorithm because of these QMA hardness results. So you can always construct very artificial instances on which the algorithm is going to get stuck. But on the instances that come out of your lab or your experiment, it seems to be working pretty well. So the obvious question is, why do these algorithms work? What are they telling us? What is the difference between the hard systems that come up here and the easy systems for which we're able to run simulations? For example, you could ask, why is it that matrix product states, polynomial size matrix product states, so these cannot possibly describe all possible vectors in d to the n dimensions? They cannot. So why is it the case that they work so well for ground states of local Hamiltonians? So at least to that question, we've known the answer for a few years now. It's a simple answer. You have to pay attention to the gap. So there's one more parameter of the Hamiltonians that we need to be looking at in order to study their complexity. So I mentioned the dimension of the particles and also the locality, as if it was obvious that it's interesting to concentrate on things that are one dimension and local. This is kind of physically obvious because interactions tend to be short range, so it makes sense to look at local interactions. So we're going to be looking at one more parameter, which is this gap. So it's intuitively, it's kind of saying how well isolated the ground state is from the other eigenstates of the Hamiltonian. So I already defined the ground state energy E0. Then we can look at the first excited energy E1. This is the overlap with the Hamiltonian, the smallest possible overlap with the Hamiltonian of a state that's orthogonal to the ground state. And we say that the Hamiltonian is gapped if the difference between these two energies is a positive constant. So I'm going to assume throughout the talk that when I say gapped, I mean constant independent of the number of particles. So dimension, local dimension will always be a constant. Number of qubits will grow and the gap will stay a constant. So now if you put this one assumption on the local Hamiltonian, that it has a gap, then we know a lot more about the structure of the ground state. So it's a very famous result by Hastings 7-8 years ago that ground states of gapped one-dimensional local Hamiltonians satisfy an area law. What this means is that the ground state is not arbitrarily entangled. If you look at this one-dimensional ground state and you cut it anywhere, the von Neumann entropy of the left or right halves will be bounded by a constant. And you can go a little bit further, build on that result, and show that as a consequence, the ground state also has an efficient classical approximation by these matrix product states that I'll describe later. In particular, because there is a classical description of the ground state, the problem is now in NP, so it can't be QMA hard. So any of these QMA hardness results that I mentioned in the previous slide only apply to Hamiltonians that do not have a gap, at least as long as we look at one-dimensional Hamiltonians. All right, so now there's this result from Sirac, Schuck, and Verstraete, which shows that, okay, maybe you have an efficient classical description of your ground state. It doesn't mean that you can find it efficiently. And what they did is they gave constructions of local Hamiltonians such that the ground state has a polynomial size approximation, but finding it is hard, at least as hard in their result as factoring. I think you can make this into a NP hard problem if you want. So we're still stuck. On the other hand, their Hamiltonian is not gapped. So the ground state has an efficient classical description, which is implied by having a gap, but their construction doesn't have a gap. So it still leaves open the question of whether this gap assumption is sufficient in order to get efficient algorithms for finding this classical description of the ground state that by Hastings' result we know exists. And so last year there was a sort of a nice breakthrough in this direction. This is a result by Arad, Kitaev, Lando, and Vazirani. They improved on Hastings' real law. They got better parameters, but as a consequence of that, they were able to show that there exists a sub-exponential time classical algorithm for finding a good classical description of the ground state. And I'll sort of give you the idea of that algorithm a little bit later because our result builds on it. Right. So one thing that their result pointed to is just the importance of this gap. Right. If you combine this plus this plus this, you see that the gap is an important condition in order to get algorithms that are faster than just generic exponential time algorithms. So at least from the point of view of computational complexity, it is a relevant parameter of the local Hamiltonian. All right, so let me describe our result now. So what we do is give a polynomial time algorithm. So the input is as I've described it before. So it's this local Hamiltonian, 1D chain, d-dimensional qubits that has a constant gap. The output is a matrix product state that has fidelity 1 minus delta with the ground state. Delta is your approximation error. You get to choose this. For most of the talk, we're going to think of delta as being inverse polynomial, like 1 over n squared or something. You can think of it as being a small constant. It's the same. Here's the running time. I'm saying polynomial time, so you can just stop at polynomial time. But if you're interested in parameters, here's what the parameters look like. Maybe I can elaborate a little bit. So one thing to observe is that if you fix the local dimension and the gap, as I've been doing, this is polynomial. It's just n to some constant, probably a pretty bad constant. But if you look at what the constant is and how it depends on d and delta, on delta it depends exponentially. So you have something that's doubly exponential in the inverse gap. So as the gap goes to 0, this constant blows up like crazy. And also the dependence on the local dimension is not that good. It's sub-exponential, but it's not a great dependence. The dependence on the error is reasonable, polynomial in inverse error. So if you want polynomial accuracy, this is going to run in polynomial time. If you're interested in better than inverse polynomial accuracy, then the algorithm is going to run slowly. And I think this is something that maybe is not avoidable. Another small comment is that the algorithm is a probabilistic algorithm. There's only one very small step that's probabilistic. I'll tell you which step later. Other than that, you can guarantee probability of success inverse polynomially close to 1 in polynomial time. You can even maybe get this exponentially close to 1. So all right, so for the remainder of the talk, I'm going to be going into the algorithm, describing it first in some simple cases and then in general. So before I did that, I thought I should give you a one-sentence summary so that if anyone feels like taking a nap right now, they can still handle the cocktail party tonight. So what's the summary of what the algorithm is going to do, right? So, I mean, in the first place, the problem that we're trying to solve is a very simple problem, right? We have this Hamiltonian. This is just a simple matrix, and we're trying to find the ground state. We're trying to minimize the energy. So it's a simple convex minimization. It's even a semi-definite program. We're trying to minimize this trace here. Rho is a density matrix that represents the ground state, and in general, so it's a density matrix and C to the end. The problem that we're facing, of course, is that this is exponential size space. So if we do it naively on our classical computer, we need exponential time and an exponential space in order to solve it. So how are we going to solve this problem? Is that we're going to identify a polynomial size subspace of the whole exponential space in which we have the guarantee that this ground state or a good approximation to it can be found. We're going to do this iteratively. So for every I is the qubit going from 1 to n, we're going to construct these subspaces Si, which are always going to be polynomial size subspace of the first I qubits, such that at every step we have the guarantee that the reduced density on the first I qubits of a good approximation to the ground state lives in this subspace. So if we do this, we carry it all the way to the end. If you plug I equals n here, what you have is a polynomial size subspace on which lives a good approximation to your ground state. Because it's a good approximation to the ground state, it must have very low energy, and you're going to find it in this way. Maybe I should mention right now, why does this find the ground state? It minimizes the energy, and because of the gap, if you have a state that has an energy that's very close to the ground state energy, then the state itself also needs to be close to the ground state. This would not be the case if your system was degenerate, for instance, right? If you had the two-dimensional ground space. But because of the gap assumption, this is enough to find a good approximation to the ground state. All right. So that's the strategy. Does it make sense? If you have any questions, we can pause for questions before I go into the rest. Is this okay? Questions on the notation? Yep.
A question about the history, I guess. So how does the result by Norbert and Ignacio about efficient polytime DMRG fit into this story?
What's the result about polytime DMRG?
They proved that DMRG can be done really provably in polynomial time.
No, exponential time.
Huh?
Exponential time.
Well, I guess it depends on what parameters.
Oh, so it's
I'm sure there's a difference.
it's exponential in the bond dimension. So
This is the difference.
no. So for instance, this sub-exponential algorithm that I mentioned just builds upon theirs. Prior to our work, there is an algorithm that achieves the same problem, and the running time is expressed a little bit differently. It's exponential in what parameter? Exponential in the bond dimension. That's kind of the amount of entanglement, or the bond dimension of the matrix. Okay, for anyone who knows about this, bond dimension of the matrix product state. Okay, what's the bond dimension of a good approximation to the ground state? From Hastings' result, you know that it's going to be linear or something in the number of qubits. So you get exponential in n. And what the result I mentioned did is improve that, just because they showed that there's better approximation to the ground state. Actually, you have sublinear bond dimension, so you get a sub-exponential algorithm. This is a good question. This is not going to improve on the size of the matrix product states or the bond dimension. It's just going to be, the algorithm is going to be a bit smarter, but it's not saying anything about how small the description is. Right. Was there there's another question actually? Yeah.
Sort of naive question, but
Good.
is there any kind of nice example of something that has a constant gap and gives you kind of quite a complicated matrix product state?
Yeah, someone can answer this, I'm sure. I tried to figure this for at least an hour yesterday because I wanted to tell you and I couldn't figure it out. So I don't know what's a sort of, take a gapped Hamiltonian, what's a lower bound on the bond dimension for the ground state or the entanglement for the ground state. There's a lot of upper bounds around. Maybe someone knows in the audience, feel free to answer. So, gapped local Hamiltonian, do we know that the bond dimension of the ground state needs to be at least something? I think we expect it to be like at least, well, we know it can be sublinear, and I think we don't expect to be able to do much more than that. Maybe. Sorry?
The product set solutions to interacting Hamiltonians. So,
but those exist in some cases, but there's also cases where we know they don't exist. Right? So this is what I'm asking about. What are sort of the worst examples, not the best examples? Okay, let's go on. So here's the outline. Let's see if we manage to make our way through it. So first we'll have a little bit of warm-up. This is going to be just a sort of a toy version of the algorithm for a completely classical problem. So this is just to think about what's going to happen, max 2-sat. Then building on that, I'll describe how this can be easily, or can be extended to this exponential time algorithm of Schuch and Sirac, of Estrada, or the follow-up sub-exponential algorithm. And then I'll move into describing what our algorithm does. So let's start by warming up with max 2-sat. For those of you who don't know what max 2-sat is, it's a classical constraint satisfaction problem. It has n variables. The variables are Boolean. They could be also take more values than 2, but just for the example, I'll assume them to be Boolean. Think of them also as organized on a line. And now we have constraints, classical constraints that tell us how these, constraints on these neighboring variables. So that's the variables. We want to solve this classical constraint satisfaction problem. So we want to find an assignment to the variables that satisfies the largest possible number of clauses. We're going to do this iteratively using this little table here to help us. So let's get started. We want to find an assignment, and I'm going to start with the first variable. There's two possible values for that variable, 0 or 1. And here I'm sort of putting a score, which is how many clauses I satisfy with my assignment. Well, so far, we haven't seen any clauses or constraints, so score 0. Okay, so let's look at the first constraint. The first constraint says that the two first variables should be equal. All right. So now we're trying to set a value for this second variable. Again, we have two possible choices, right? Either 0 or 1. This is why my table has only 2 rows. So if we set x2 to be 0, then the best possible choice for x1 is 0. The constraint is satisfied. I score 1. Okay, this is all good and simple. Here, if I set x2 to 1, I also want the first variable to 1, and then my score is 1, and then I'm done, right? All right, this first constraint was not so interesting. Let's look at constraint number 2. So now we're going to try to fill up values for x3. Again, we have two possible choices, 0 or 1. Let's look at the constraint. This is what it's saying. Okay, what if I set x3 to 0? Then not x3 is 1, and the constraint is saying that x2 should be 1. So in my table, at every step, I'm going to keep an assignment to all the variables that I've seen before for each possible value of the latest variable. And that's it. So there's two possible values of the latest variable. That's why I have 2 lines. So for x3 being 0, I want x2 to be 1, meaning that I want to be using this second line here. So I'm going to copy it up there, like this. And now I'm satisfying 2 constraints. And then we look at the other possible value for x3. x3 equals 1. Well, in that case, the constraint is, it's lost. I mean, this is 0. We can't satisfy this. So I could put to the left of my x3, either keep what I have right now, or put the other possible solution, which was 0, 0. This is not going to increase my score. So this is where I'm standing. So I repeat this all the way till the end, and then I find a solution, and I have 2 solutions, and I choose the one that has the highest score, that satisfies the highest possible number of variables. Okay, so I'm not sure if this is completely clear here. What we did is that we said that, look, as you go along this chain, choosing values for the variables, it's not necessary to keep all possible assignments of the previous variables that you've been looking at, right? There's only ever 2 lines. If we tried all possible assignments, we'd have 2 here, but then 4, and then 8, etc. What's making this possible is that what we're trying to achieve is find the assignment that satisfies the maximum possible number of clauses, right? And when we look at a certain step here, and we're wondering how many clauses can we satisfy, well, we can decouple that into 2 problems. There's how many clauses we're going to be able to satisfy to the right of x3, and how many clauses we're satisfied to the left. All right. How many clauses we can satisfy to the right, this only depends on the value of x3, not on anything that's happening on the left, because no clause acts across here. This is where you use the 1 dimension. So you only need to know, what is the value of x3 in order to decouple this problem. And then to decide what is the half on the left here that you should choose, that you should plug into x3, well, you just plug in the one that satisfies the maximum number of possible constraints for the left. So because you're keeping this score in your table, when you arrive here, you just choose among the left tails, which is the one that when you put it and you choose this value of x3 has the highest score. And you do this for all possible values of x3, and by doing this, you have the guarantee that you're going to find the best solution. So we have a very nice, very easy linear time algorithm that solves 2SAT using this decoupling property that's guaranteed by the fact that the problem is 1-dimensional. Right, so that's the important point here. So the question is whether we're going to be able to extend this to our problem of interest. It's still a 1-dimensional problem. It still has these constraints. There's one obvious major difference is that what we're trying to do is trying to find this quantum state, this ground state. And this ground state is not going to be a product state. There's going to be entanglement. So this decoupling that I'm doing here, it's not clear anymore that you're able to carry it over to the quantum setting, because how are you going to handle the possible correlations that may be in your ground state between these qubits and these qubits. So I want to describe how you do this. Using these matrix product state representations. So I was sort of guessing most of you might already be familiar with them, but just in case, I'll describe what a matrix product state is, at least at an intuitive level. So I'm going to have pictures, and I think you should be able to follow everything just by staring at the pictures and having some vague idea as to what they represent. So this is a matrix product state. This is how I'm going to represent quantum states on n d-dimensional particles. So each of these legs here, that's a q dit. So it's a d-dimensional leg. These are tensors. So this one is a matrix, D by B, and these are tensors. It's like a 3 matrix, like a box, that has dimensions B and B and D. And that's how you represent the state. So how do you compute the state from this? You just match all the B-dimensional bonds together, you multiply them, and you get now something that lives on CD, tensor CD, etc. And that's the representation for your vector. For example, if you take B to be equals to 0, then each of these circles is just a vector. It's just a d-dimensional vector because the other 2 dimensions are 0. And in that case, what you have is a product state. And what this d-dimensional vector is, it's telling you the coefficients of the first qubit on the canonical basis for this d-dimensional space in which it lives. In general, if you allow B to grow, be slightly larger than 0, then this is a way to represent the correlations that go across your state. It's saying that there's some interaction between these qubits, and these interactions are represented by this bond here. Right, but pictorially, I think it's sort of intuitive. You have this these qubits dangling down here. And so we're trying to extend this algorithm that I was describing in the previous slide. So we're trying to extend this decoupling approach. So what we want is find a matrix product state that minimizes the energy of the local Hamiltonian. So the energy of all the terms is just the overlap of the vector on the Hamiltonians. I can split it into 2 terms. It's linear. It's the energy of the first I minus 1 terms plus the energy of the remaining I terms. And what we're asking is whether this computation can be decoupled. Is it the case that this energy here can be written as a function of only the first few tensors up to the ith one, and this one as a function of the remaining tensors? This is exactly what we had in the previous slide for the classical problem. So we can almost do this. It's going to be good enough for our purposes. Let me show you why this is possible. So let's take a Hamiltonian, one of those from the left. I could take H1, but let's take one that's a little bit harder, one that acts on the border here. You want to compute the energy of this, so we're going to compute this overlap. So pictorially, I'm just taking my state. It was acting on the left, putting it acting from the right, and then closing all the bonds that are open. That is exactly the energy of my vector, my MPS, with respect to this Hamiltonian Hi minus 1. And now, just because of normalization, I haven't said this, you have to believe me here, but the way these matrix product states are normalized, it will always be the case that this evaluates to just a trivial identity, so it collapses to this. So this is saying that to compute the energy of any of the Hamiltonians to the left, you only need to know the left part. That's a consequence of normalization. It's sort of a triviality. There's no worries here. The worries are more for the right-hand side. So now if we're trying to evaluate, let's say, this Hamiltonian, which also acts on the right, we do the same thing, we sandwich it. Now we'd want to collapse all the left as I did before, but this normalization you can't enforce from the right. You cannot enforce it from right and left at the same time. You would have a trivial matrix product state. What you can do though is collapse this thing. You can contract the network and look at what is the contraction that you get here. And the nice thing is that even though this here was a big object, you have a lot of high-dimensional tensors potentially, the contraction is very small. It's just, something that has d-dimensional legs here and b-dimensional leg here. In particular, if you want to discretize this space, you'll be able to discretize it using an epsilon net of a reasonable size. I'll get to that a little later. So that's the picture that we have in mind, and this contraction here is going to be what we placed just the ith variable before. It would have been nice if I had this, let's see, I had it, here just ti, but this picture is just telling us that we have to replace ti by something that's very close to ti. It does depend on all the information that we had before, not only the ith tensor, because it's a part of this contraction, but it is a small object, the same size as ti. And that's what's going to be important to make the algorithm. So we saw this already. All right. So let me try to describe a sub-exponential algorithm here, or even the exponential algorithm, exactly in the same way as I described the max 2 sat. Maybe review it, it'll make things a little bit clearer. So the input is always the same input, it's our local Hamiltonian. Our goal is to find a ground state represented as this matrix product state, and we're going to do this by filling in a table from left to right as before. Only difference is it has a little bit more rows. It's going to end up having exponentially many or sub-exponentially many rows. All right, so we do it as before. We do it one tensor at a time. So let's suppose that we've arrived at a certain step. I've found here up to the I minus 1 tensor. I found a description for the left half of my state. Actually, I found many of them, one for each possible. Before it would have been value of ti minus 1. Actually, now it's one for each possible contraction that is in this delta net or epsilon net that we had before. And I all list them here, and I list their energies. how do we go one more step, right? That's the question. So to do one more step, we're going to iterate over all possible contractions for the next tensor, and for each contraction we want to find the best half among the left halves, so the one with the minimal energy that matches that contraction. All right, so we have a contraction in mind, and then we look at all these left halves here, we look at their energy, we contract them, we compute the tensor, and we check, does it match this? Yes. If it does, among all those that do, which is the best one? And then we plug it in. We save it like this. We put a tensor, and then I update my energy with the best energy. And then I do this for all the entries of my table, and then I just repeat this iteratively. And the decoupling property that we saw in the previous slide is guaranteeing that for the contraction here, among all these contractions, there's one that is going to be the one of the actual ground state, over a good approximation to the ground state. That there is such a contraction for the ground state is something that's guaranteed by the area law, which says that the ground state has a good approximation with small bond dimension. So we know that one of these contractions in the column is the good one. We don't know which, this is why we're keeping all the tables. But for the one that's good, we're finding the left-hand side that has the minimal energy and that matches it. And that's as good as we can do. This is going to correspond to the same energy that the actual ground state would have given us. And then we proceed from there. This is why we have the guarantee that this is going to arrive at the correct result. So what's the running time? Well, basically I have n steps, right, very roughly, and each step is taking me roughly the number of lines for the size of my epsilon net on the number of contractions. This epsilon net was to discretize what's a priori a continuous space, right? And the size of the epsilon net is exponential in the number of dimensions. So the running time depends very much on what is this bond dimension, the sort of line that goes across the matrix product state. What bond dimension I need to take, this is something that I have from the area law. It depends how good the area law is. So if you take Hastings' area law, you get a bond dimension. I wrote n squared. I'm actually not quite sure. Maybe you can get it down to n, but then you get this parameter raised to the n, so you get an exponential time algorithm. And what Arad al did was improve the area law. So if you try to parse this, it's something that's less than n, so it's sublinear. This is why you get a sub-exponential algorithm. It is the same algorithm. You just have an improvement in how large you need to choose this bond dimension. So I wrote this here. This is kind of big answer to Ashley's question. I actually don't know for a fact that this is true, but I think we don't believe that this bond dimension can, even for the systems that I'm considering here, the gap system, be brought much further down. So in general, we don't expect that there's a better B, and so if we carry out this strategy here, we're kind of stuck. I mean, there's no obvious improvement to it. We have to do something a little bit different. Presumably, abandon this idea of keeping one line for every possible contraction. We have to be a little bit smarter. So this is what we're going to try to do for the remaining time. Now I'll move on to describe how our algorithm proceeds. Do you have questions? All right. It's actually not going to, I'm sorry. So before describing the algorithm, I want to introduce sort of an important concept in the algorithm, which is what we're using in order to avoid doing exhaustive search. I mean, the basic idea is that here you're discretizing space and you're searching over all possible elements in your discretized space. And we're throwing away the fact that the problem that we're studying is a problem of linear algebra. And in general, if you have an exponential size space, discretized space, this can be the result of, you could potentially be able to describe it much more efficiently just by choosing a basis. You have a polynomial size basis, that gives you an exponential size space once you discretize it. So I'm not saying it's automatic, but this is what we're going to try to do. We replace discretized vectors by a linear basis. So this is an important definition of viable set. What's a viable set? Maybe I should, well, okay. So it has three parameters, I, delta, S. I is a qubit, delta is an error, S is a size, the number of vectors in the viable set. So in general, for some I, it's going to be a subset of the space on which live the first I qubits. And it's a subset that has the guarantee that when you look at the ground state, and you look at the reduced density of the ground state on the first I qubits, or let's say the left Schmidt vectors of this ground state, then they live on the span of my space. So this is the sets, if you remember when I first stated the theorems, this is the sets that we want to be constructing. They are the sets that contain, are guaranteed to contain good approximation, left half of a good approximation to the ground state, right? So morally, this is just a vector space, so it's a basis, or not a basis, generating a family for a space in which the Schmidt vectors live. Right? So important definition. Okay, and one observation follows from the area law is that if you fix a qubit, any qubit, and you fix a error tolerance delta, then there exists such a variable set such that the size is pretty small, it's just polynomial in the inverse of delta. Right? So if you take delta to the inverse polynomial, which is what we were doing before, you get a polynomial size set. If you take delta to be a constant, you can get actually a constant size set. Because for any bond, any one bond, you can make this bond have constant size for constant approximation. The others you need to remain polynomial, but just the one bond you can make constant. That's something important that we're going to be taking advantage of. So we want to construct this, right? We want to construct this plane for I equals n, because then we'll be done. Provided there's caveats, we continue to present these vectors efficiently, and we optimize over them, putting this under the carpet, assuming that it's true. If we have such a set, then we'll just know that we can find the ground state on that set, and because it's represented by polynomially many vectors, we're going to be able to do this convex optimization to minimize the energy over the set. The question is how to do with that set, right? And we're going to come up with it iteratively, sort of following along the lines of the previous algorithms, but trying to improve a little bit. Okay, so here's the outline. Three-step algorithm, and I'll describe each of the 3 steps. So we're trying to construct these variable sets. When you start, 0 variable set is not good. It doesn't even involve a qubit. This is trivial. You just initialize it to anything you want. And so let's suppose that we've managed to come through the first n-1 steps of the algorithm. So we have such a variable set. I wanted to say before, but I forgot, why do I always think error inverse over n squared? Because this error here, maybe you should think of it as the error that you make at every step. Because you have n steps, you want n times delta to be small, because it's going to be the final error, right? It could be a constant over n or n squared, something like this. But that's the value that I'll keep throughout. Okay, we have this, and we want to move one more step. So we can do it in. So sorry, this is how it looks like, right? We just have these vectors. Each of them is represented by a matrix product state, and we go them from the first element to the qubits. And now we want to extend this by one term to the right. First step is something trivial. Is we say, well, we don't know what this next qubit is supposed to do, so we take all possible values. So I extend my thing a little bit, and each of my states here I extend in all possible ways, so meaning that I tensor with the basis of my next space. So I have d vectors, each of them I tensor them with the d possible. So it's the canonical basis for c to the d. Right. So this is the same approximation guarantees as before, because I extended it by basically including everything I could include. The problem is that the size grew up, right? I multiplied my number of vectors by d. If I was to do this n times, I'd have d to the n, just the basic algorithm. So the next 2 steps are trying to reduce this size. Actually, the next step is going to reduce the size. And the way it's going to do it, I'll explain this more in the next slide, but just very roughly, we're going to reduce the error here, have a big loss from delta 1 over n squared to 110 by sort of focusing on contractions. So these contractions come back, but now we're going to be looking only at contractions that have a constant one dimension between I and I plus 1. We're going to look at each sub-possible contraction where b is going to be a constant. We're going to look where there's going to be only polynomially many such contractions, a fixed polynomial, depending on content, and that's it. And for each contraction, we're going to find, on our set, kind of a bunch of vectors or vectors that's supported on that set that matches the contraction. A bunch of these MPS together, we contract them, we try to find a combination that matches the contraction. We can find many of them, and with many of them, we choose the one that has the smallest energy. We have to check whether it can be done efficiently, right? Because that's external. And that's the only one that we keep. We throw everything out. Everything else out. The result of that is that now the new size of my set is something that's independent of what it was before. It doesn't matter. It could have been huge. As long as I can optimize over it, I get something that's pointable size but independent of the other. This is good. We have a blow up, but now we reset this. There's one problem though, is that we get a lot of errors. This one is too much. People are saying, well, because 1 over n, because this thing is going to blow up. This is not something that you can withstand at every step. Basically here, what I'm doing is in a way I'm trying to find a good approximation that has constant one dimension. I don't can do this better, and that's sort of the main optimization maybe is you can improve the size is going to increase polynomially, not too much. It's okay to do repeatment now because this was, you know, just two fixed polynomials, but repeat it to something fixed, and I'm calling this fixed thing x and x is going to be very. I really put the error from 1 to 2, set it back to this squared here by applying number 1 mixing coupling and exponential algorithm, which is sort of straightforward, but then we roll it what's more. So this is the model we're trying to achieve. I delta by this factor. So we reduce the size at the cost of increasing the where the ground state. The big factor we're using is this improved Fourier law. It follows, it doesn't follow the Fourier law, but it follows. It has one dimension across I and I plus 1, which is the thing that we're doing. It's polynomial in inverse of the error. The other bond will be large, it will be polynomial size, but this one bond we can make one more step here. That was step 2. Let's look at step 3. Step 3 is this. Now that we've blown up the error, we want to make it better. We're willing to suffer a little bit in how many vectors we have to So the tool that we're going to use is something that was introduced in the previous paper, the improved real law paper. It's called the proximate ground state projection. Like the spelling was the proximate ground state projection. It's something that we're going to construct from the local Hamiltonian. It has 3 important properties. The first important property is that it's a local operator. So it's a big matrix, called the matrix A, that you can decompose as a product of AJs, where each AJ is local. If you look at this is my usual matrix product state, it's going to look something like this. You know, A1, A2, and then maybe A3, A4. So this is how A looks like. Right? It's a bunch of local matrices, and you apply them in a product like this. It's going to have this layered structure. 2 other properties. One is that it leaves the ground state invariant. So when you add to the ground state, nothing happens, it stays. And then the other is that if you take something now that's orthogonal to the ground state, it tends to kill it. So it decreases the norm by a constant factor. Constant factor depends on the gap of the local Hamiltonian. So this thing here is something that we're going to construct from the Hamiltonian itself. And if I'm allowed one more slide, I'll show you how you. It's a very simple construction in the next slide. But let's assume that we have such a thing. Let's see how we can use it to achieve this step here. Right? It's actually pretty simple. So what do we know from this here? we know that there exists some vector on the whole space such that this vector is a good approximation to the ground state. So I can write it something like this, right? It's not so good, but it's decent. And if I look at the left Schmidt vectors of that state, they live on my space Si. So they're among all these matrix product states, or at least they're linear combinations of these matrix product states that I had before. So now as a thought experiment, let's imagine applying this AGSP to this reasonably good approximation gamma a number of times that depends on the target approximation. Then just because of properties 2 and 3, I renormalize here, but the component on the ground state will stay the same. This component will be killed down, so if I apply it enough times, I get something now that's a much better approximation. But I don't know what gamma is, right? Remember, I only have this set which is guaranteed to contain the left half of gamma, so what we want to do now is morally apply this local operator A to each of the vectors in our set, because we know that gamma has its left half in there, so if we apply A to each of the left halves, then A applied to gamma will also have its left half in the set that we obtain Si. And this is how we're going to improve this. There's one small problem on the picture. If you look at this A is not something that you can so straightforwardly apply to stuff that is only on half of the space. I mean, sum of A is like over there, and that's fine. But sum of A, like this guy, is asking for something you know, and you want to be applying this. But here you don't know what is this. I mean, that's the next step. We're trying to figure it out. So we don't know how to apply this operator. There's a simple fix. This is just a d squared by d squared matrix. You can decompose it into a linear combination of d squared terms. And then instead of just applying this, which you'd like to do, well, you're just going to apply bk for each possible value of k. There's a constant number of possible values. And you keep all the vectors that you apply, one for each bk. So this is why the number of vectors that you have in your variable set tends to increase a little bit just because of this issue here. And you have to make sure that, you know, as you do this, I mean, it depends how many times you're going to do it, but because it's only logarithmic, the number of vector blows up by a constant every time we have this phenomenon. Overall, we only have a polynomial blow up. So that's fine. We haven't increased the size of our set by too much. So that's how you improve the error. And maybe I have 5 more minutes, or yeah. So I'll just give you an idea of how you construct this. There's actually different constructions. In the paper that introduced it, they have very sophisticated construction. This is one of the key ingredients in this improved real law. Here we have a much more simple construction that suffices for our purposes. So I can describe this very easily. Oh, I mentioned this before. As you do all this, you're working with these matrix product states, applying matrices, and there's a question. I mean, aren't you blowing up the bond dimension of these matrix product states? Can you still keep polynomial size descriptions? If you do it naively, no, you don't. You end up having very large states, and this blows up all the time. So there's one more step that I'm not describing in this state, where you argue, again using the real law, that it's possible to cut down on the size of these matrix product states and always keep them polynomial size. This is kind of a standard step. It's something that you have to be careful with, and I'm not describing here. All right, let's construct this thing. So let's just think about frustration-free case because it's easier. So let's imagine that the lowest energy is 0. So this ground state is left as h times the ground state has 0 energy, and then the orthogonal states orthogonal to it have some constant energy delta. Here is one way to construct something that satisfies properties 2 and 3. That's pretty simple. Just take your Hamiltonian, divide by n, identity minus it, and raise to the n. Okay, let's check what this does, right? If you take the ground state, this does nothing to it by this. The identity is the identity, so it's left invariant. If you check what it does to something that's orthogonal to the ground state, well, this component here is going to multiply it by 1 minus delta over n. Then you raise to the n, so you recover something that's shrunk by e to the minus delta, roughly. So roughly, you get this shrinkage for vectors orthogonal to the ground state. That's just a straightforward calculation. Right, but this doesn't really look like the form that we want before. Is this local? Well, one thing you can do is you can expand this, right? So you can think of this, what's 1 minus h to the n? 1, I can write as n identity divided by identity. So now I have at the denominator 1 over n that I can pull out, 1 over n to the n. Numerator, I have n times identity minus my n hi's. And so I write it like this, identity minus h1, identity minus h2. So I have these n terms. And now, sorry, there's normalization missing here, but I can, oh, there's a lot missing, I'm sorry. There's a product missing, right? So this should be raised to the n. This not, it's already, but this should be raised to the n. So because it's raised to the n, now I can expand it, and I get a very large sum, exponentially large sum of simple products. Now these operators are local, right? They're just identity minus my local operator is just the sort of complement projection to hi. So each of these is a local operator, but I have an exponentially sized sum of them. So this is way too many. Right. So what we're going to do about it is simple, just subsample. So what we're going to argue is use the concentration bounds for sums of IID matrices, matrix value turn of bounds, to argue that this exponential size sum, because each of the terms here has a reasonable norm, and what we're interested in really is these two properties. We don't want to have, a very fine, we're not doing anything very fine-grained here. We just want to preserve this one vector, and then the orthogonal space we want to shrink by a constant. If it's not exactly that constant, it's fine. So these matrix value turn of bound let you argue, I'm not giving the details, that if you just sample at random a polynomial size subset of these exponentially many terms here, you get something, and again it should be normalized, that's a good approximation to the original operator. And now it has the locality properties that we want. I mean, each of these is local and there's only polynomially many, and that's good, good enough for our purposes. So I mentioned this when I started. This is the only step that uses randomization. So I completely expect you could de-randomize that part, make it more efficient. We didn't really worry about that, but this is why I said it's a randomized algorithm in the first place, just to construct this operator here. Yes?
If you use the approximate ground state projectors from this paper, you use Chebyshev polynomial construction.
Doesn't that get rid of the randomness?
No, so the problem is that we can talk more about this later, but their construction, the way they do it with these polynomials, what you end up with is something that's local in a neighborhood of the bond that you're interested in, but not to the left or to the right. Right, we don't care. Sorry, you're right, we don't care. Left, it's not either. And so you can't control. You apply it a few times, like we do log times, and you don't control the size of your MPS anymore. Something they didn't care, because you only care about this one bond, but we want something efficient across the whole left half. So. Okay, so let me just go over, we've been over this before. I just summarize this algorithm that was in 3 steps. So we're building these variable sets that are guaranteed to contain the left Schmidt vectors of a good approximation to the ground state in 3 steps. There's the extension step that was pretty trivial, just include everything that you could possibly include. Then there's a reduction step that reduces the size, and this used the area law in a crucial way, right? It used the area law to justify the fact that area law for this decoupling property justifies the fact that among our set, we have a lot of candidates, but we can really focus only on one candidate for each possible contraction, and we have few contractions to be looking at. Unfortunately, this blew up the error, so then there's a last step which improves the error, and in order to do that, we apply this approximate ground state projection, which is something that you can construct, but it uses the gap property of the Hamiltonian in order to construct it. So we're using the gap property here, and we're also using it here through the area law. All right, in case of conclusion, I don't have much to say, maybe just questions. I mean, there's a lot of questions of where you can take this. One question is, in practice, if you look at DMRG, this algorithm that I mentioned before is something that achieves the same problem. It's the same thing, but it's not guaranteed. It's very efficient, much more efficient than if you were to implement what we did. So, I'm not suggesting that you should be using what we did, but I'm suggesting that maybe by thinking a little bit about it, you could come up with improvements to DMRG. For instance, this idea that you can, when you do the local optimization, satisfy yourself with something that has only a very rough approximation, and then you can maybe sort of efficiently improve this approximation quality. Once you have a rough quality, you can improve it by applying the AGSP, maybe, Another question is whether you could come up with an algorithm that's fully local. If you think of this as some process that nature is doing. I mean, nature is sort of converging to the ground state of your local Hamiltonian. Nature is local, right? It's not doing stuff at the one and at the same time. And our algorithm is almost local because it's looking at the ith qubit, but not quite, because in order to decide which vectors we were keeping for the left-hand side, we chose the ones among those that match the contraction that have the smallest energy. And this smallest energy is the energy of all the left-hand side. So it's a little bit non-local in that sense. It's a question whether you could make it fully local. Presumably this would be this would be a nice, elegant algorithm. Sort of the major open question about these algorithms, about the area law also, is whether you can go forward from one-dimensional system to two-dimensional systems. Of course, I have no idea about this, but you could ask if the kind of tools or ideas that are developed here have any bearing into the problem for 2 dimensions. I think that's a kind of research direction that's interesting. All right, so that's all. Thank you.
Thanks very much. Any questions?
Suppose you apply your algorithm to, well, because in practice, I mean, you're given a Hamiltonian, you don't know if it has a gap or not, right? So suppose you apply your algorithm blindly, I mean, could you somehow detect while you're running it that it has a gap smaller than you thought, or?
Yeah, it's a good question. You could ask, can you use this in order to estimate the gap, for instance? So it's a good question. I don't know. The algorithm, if you don't do anything, it'll run. It has no stopping criterion, so it'll run and it'll end up with something. If you know what's your target ground energy, then you can look at what's the energy of what you found, and if it's not close to the ground state energy, then you know there wasn't a gap because something went wrong, right? But if it's close to the ground state energy, then you don't know, because it could be that you found, it could be that there's no, in that case it could be that there's a gap or that there's no gap. A lot of things might go wrong if you don't have a gap, but it's not that you would see what's wrong. Like, for instance, you'd find, when you're looking at these contractions, something fishy would be, no, I don't see any such thing. So this is a question whether you could use this also maybe to detect if there's degeneracies. What if you're running it on something that's gapped but has degeneracies in the ground space? Are you going to be able to detect this degeneracy because, for instance, you'd find different states running at different times? But I don't know. It could be that you always find the same state even though it's degenerate. There's interesting questions in that.
Sorry, so the gap is part of the input in a sense. Like you need to know kind of to when to stop. Based on others.
No, the gap is well, I mean, these things you can always, you don't need it to be. You could always say, let me run the algorithm with gap equals to 1, and then 0.5 and then 0.25. And then if it always gives the same result, then it's fine. If you see the result changing, you detect that you're not. The only place where you need to plug in the gap in the description of the algorithm is how you set up your approximation error parameters, because you want them to be sufficiently low with respect to inverse gap. So if you have a sort of rough lower bound on the inverse gap, you can plug that in, you make the algorithm slower. So you'd want to start with roughly, yeah.
As on those two, I mean, that comes back to Miguel's question, right? Because if you could detect whether the algorithm was succeeding or failing, you could just do binary search on the gap.
Yeah, right. So So once you find something that has a certain energy, if you don't know anything about the energy that you're trying to find, then you don't know if it's correct or not. That's true. And so you don't know if your guess for the gap was correct or not, and that's correct. So yeah, fully rigorously, you need to have a trusted lower bound on the gap in order.
I'm ignorant about matrix product states. That's why I'm asking this. So, yeah, when you have a gap, then you can prove that. Well, you can have this promise that you don't have to go to really high bond dimensions to approximate the ground state, right? But what happens if you are not interested in approximating the ground state?
Sorry, what happens if what?
If you're not really interested in approximating the ground, for example, if it doesn't have a gap, the question is kind of meaningless. Who cares, right? About if it's a continuum or something like that. But can you approximate the energy with low bond dimension?
No, I think this is even not known. Maybe someone will correct me if I'm wrong, I hope, but in the case where you have a gap but the ground state is degenerate. Not sure if in that case we definitely don't know that there is a basis for the ground space where all the vectors have low bond dimension. I don't even know that we know that there is a state in this ground space that has low bond dimension, if it's degenerate, but there's a gap. And so in the case where you're saying there's no gap, do we know, I think your question might have been, if there's no gap, there's kind of something continuous or small gaps, do we know that there is a state in the low energy regime that has small reasonable bond? I think we don't know.
Even Matt's result makes use of the fact that it's not degenerate in ground space.
That it's not degenerate. Yeah, right. So So in both cases, either gap but degenerate, or no gap, maybe not degenerate. Then I think we don't know. They're good questions. I mean, or not that I can tell you if it's good or not, but I think they're interesting questions.
All right, and I guess thanks to them again.